Hey, welcome back to your favorite pre-calculus course. This is section 4.2, properties of rational functions. We'll talk about the domain and your asymptotes of rational functions. So let's talk about what a rational function is. Rational function is simply defined to be one polynomial over another polynomial. Get my pen here. So you got a polynomial on top, you got a polynomial on the bottom. Here's some examples. 2x squared over x plus 5. This is a rational function. You got the polynomial in the numerator. You got another different polynomial in the denominator. This is a rational function. Now, if you're finding the domain of a rational function, what you want to do is take a look at your denominator and just figure out what can x not be. In other words, what makes that 0? Because we know we cannot divide by 0. And that's going to be your problem child. So you're like, well, this part cannot be 0. Subtract 5 on both sides. So x cannot be negative 5. So x such that x cannot be negative 5. Or if you're going to do that in interval notation, negative infinity up to 5, do not include the 5 union and then take off from 5 to positive infinity. It would be the interval notation for saying the same thing. X cannot be negative 5. Second one here, 1 over x squared minus 4. Notice we want to factor that thing so that we can take a look at the linear factors. So you have x plus 2. So x cannot be negative 2 because we'd have negative 2 plus 2 right here, which make it a 0. 0 times whatever on the bottom is 0. And then right here we can't have a 2 because 2 minus 2 would be 0. So that domain just cannot be negative 2 or 2 there. The C, part C there, you notice you got x squared plus 1. If you think about that x squared, first of all, x squared plus 1 does not factor. So you're stuck there in terms of trying to factor that thing. But is there any x value for which this thing is undefined? Well, if you think about x squared is always going to be positive. Whatever you take and you square that number, it'll always be positive. And then if you add 1, it'll just be whatever that number is plus 1. So you can never get a 0 on the bottom. So this is simply a set of all real numbers, or if you want to put an interval notation, negative infinity to infinity, or set notation, x such that x is an element of the real numbers. All those are expressing. You have no restrictions on your domain. Part D there, notice that you have x squared minus 1 on the top and x minus 1 on the bottom. So again, you're looking at that x on the bottom there and you say, well, x cannot be 1. That's your problem child there for your domain. You just look at what x cannot be, what makes it a 0 on the bottom. Let's say we're graphing a rational function here by point plotting. So we plug some points in, and first of all we say, well, x cannot be 0. First of all, right? X cannot be 0 because we can't divide by 0. So as 0 we're undefined. We can plug 1 in, 1 over 1 squared is 1. Plug 2 in, 1 over 2 squared is a fourth. Plug 3 in, 1 over 3 squared is a ninth. We could go in the opposite direction, negative 1. Negative 1 squared is 1, so 1 over 1. We can plug in negative 2. Negative 2 squared is 4, so I got 1 over 4. Plug in negative 3. 1 over negative 3 squared is a ninth. Anyways, we start plotting these points. We got the 1, 1. We got the 1, 1, we got the 2, comma, fourth, we got 3, comma, ninth, even lower. We could keep going on this thing. 3, comma, ninth, 4, I'm having troubles here. 4, comma, 16th, we could plug in a half, which would be 1 over 1 half squared, so 1 over 1 fourth, 1 squared over 2 squared. Multiply by the reciprocal on that, so keep change flip on that, and you've got 4. So this ends up being 4, 1 half, comma, 4. There's your point. Plug in negative a half, also get 4, and so on. Plug in 1 fourth. Now you got 1 over 1 fourth squared. So we got 1 over 1 16th. Keep change flip again, so multiply by 16 over 1. So we got 16, 1 fourth, anyways, way up here. And what you start to see is as you approach 0 from the right, if you keep going down, this thing's just going to keep shooting this up, okay? As you approach 0, in other words, as we pick points closer and closer to 0, you know, I picked a half, then I could pick a fourth, I could pick a fifth, and I'd get 25. As I pick points closer and closer to 0 from the right, it's shooting this up. I'm going higher and higher, my y values. Okay. Same thing on the left. As I pick x values closer and closer to 0 from the left, it just shoots us up. Okay. So that's what your function, rational function 1 over x squared looks like. We use that as a parent function to take a look at the transformations here. So we've got this plus 1 on the end, so this is just going to shift it up 1. And now we've got the composition x minus 2 in there, substitute in for x, so that's going to take us right 2. So it looks exactly the same, except this thing is moved right 2. So here's your right 2, move this whole thing over right 2, and then it bumped it up 1. Shift the whole thing up 1. All right, let's talk about horizontal and vertical asymptotes. First of all, vertical asymptotes mean that as you approach, so similar to the y equals 1 over x squared, if you, as you're plugging x values in, if it's shooting you, you're plugging x values in closer and closer and closer to 0, if it shoots you up like that or down like that, that means you've got a vertical asymptote there. And in the case of 1 over x squared, it was a vertical asymptote of x equals 0. Okay. Whereas a horizontal asymptote means as your x increases in magnitude, so as it shoots to infinity or negative infinity, if you're approaching some y value, and I'll give you some pictures of this and some examples, if you're approaching some y value, you've got a horizontal asymptote there. So here's your picture of the horizontal asymptotes, but again, I'll give you some examples, some solid examples with rational functions. Notice here, as my x's gets larger and larger and larger, the y values are approaching. Let's say this is like 1, y equals 1. As I shoot out, I'm getting closer and closer to 1. And on this function, as I shoot out to the left, as I follow the function to the left, it's getting closer and closer to that line, y equals 1. With the vertical asymptotes, as I follow it, in this case, as x gets closer and closer to whatever this c value is, it shoots me up. Okay. This one's shooting you down. Again, it just has to shoot you up or down, and you'll have that vertical asymptote right there. Okay. So here's some examples. And our oblique asymptote. So this is another way to say this is a slant asymptote. So in this case, you're not approaching a single number, and you're not just shooting up to infinity. It's approaching some, in this case, a linear line. As x goes out, it gets closer and closer to that slant asymptote. Okay, so whatever the y value is there. Okay, so what we want to do in locating vertical asymptotes is we want to factor it and find your zeros of your denominator. Make sure it's in lowest terms. Factor it, put in lowest terms. And we'll do some examples right here. So let's do this first one right here. What's your vertical asymptotes? All you got to do is take your denominator and say, well, x minus 1 cannot be 0. Add 1, x equals 1. That's our vertical asymptote for the first one, x equals 1. I don't know exactly what this looks like, but it'll never touch x equals 1. That's our vertical asymptote. B right here. Make sure you factor that. So you got r of x equals x over x minus 2, x plus 2. Your vertical asymptotes here are, where is x equals minus 2 equals 0, so at x equals 2, and you've got the other factor, x equals negative 2. So on that one, you have it at 2 as a vertical asymptote, and at negative 2. Again, I don't know exactly what this function looks like, but we'll just say it looks like this. You're never going to touch those two vertical asymptotes. Okay. C, if you notice, has got, let me erase a little bit of this. Now notice on C, x squared plus 1 does not factor. There's no way, there's no x values such that it makes that denominator become 0. So on that one, you have no vertical asymptotes. Okay, D is kind of interesting. That one's not factored. Again, let's factor it. Factor the top, factor the bottom, and what you notice on this one, let's see, what's that factor? X plus 7, x minus 3. Now the interesting thing here is it's not in lowest terms. In other words, these two can cancel. And anytime you have two that cancel, what that means is this function, the original function does not have two that cancel, right? But what happens is x cannot be 3, but you don't have a vertical asymptote there. What that means is you have a hole. And we're going to talk about holes in the next section, but it's not a bad time to introduce that. Okay, so what's happening is when you put it in lowest terms, in other words, when you cancel factors, that means you have a hole there. You're not going to have a vertical asymptote. Okay, your vertical asymptote will be the zeros of your denominator. So you only have a vertical asymptote for this one at -7, and then you've got this hole at 3. Okay, so at 3, again, you got this hole. So it's open hole again. I don't know what this thing looks like, but we'll say it looks like this. Okay. Anyway, so a hole if they cancel, vertical asymptote for the zeros of the denominator. We'll talk about more holes more in the next section. As for horizontal asymptotes, what you want to do is you want to take a look at your degree of your numerator. Okay, so what's your degree of the numerator? We're going to call that n. And what's the degree of the denominator? We're going to call that m. If the degree of the numerator is less than the denominator, automatically y equals 0 is your horizontal asymptote. If they are equal, if the degree of the numerator is equal to the denominator, what you do is you take the leading coefficients, and that's your horizontal asymptote. And then anytime n is greater than m, there is no horizontal asymptote at all. Anytime the degree of the numerator is greater than the degree of the denominator, there's no horizontal asymptote. And then we'll talk about what that means here. Let's do some examples. For instance, right here, you've got, what's the degree of the numerator? The degree of the numerator here, so let's start with our horizontal asymptote. The degree of the numerator is 4, so that's our n. The degree of the denominator is 3, that's our m. So obviously 4 is greater than 3. There's no horizontal asymptote. Now if you look back at that slide, anytime that it's only one more than the bottom, that means you'll have a slant asymptote involved there. Okay, so it'll approach this linear line. So what you want to do is you want to do the long division, take 3x to the 4th minus x squared and divide it by that denominator. So let's do the long division here. I'm going to put 3x to the 4th. I'm going to put in a placeholder 0x cubed minus x squared plus 0x plus 0, and I'm going to divide that by x cubed minus x squared plus 0x for a placeholder plus 1. And then I'm thinking, what times x cubed gives me 3x to the 4th? I'm trying to match that 3x to the 4th, and I know it's 3x, so I put a 3x right there, multiply through 3x times x cubed, 3x to the 4th. 3x times negative x squared, negative 3x to the 3rd. 3x times 0x, 0x squared. 3x times 1, 3x. And don't forget to make sure you subtract that whole thing, just like we did in the old long division algorithm with arithmetic. So we change all our signs. So change that sign, change that sign, change that sign, change that sign. All right? Those are gone. 0x cubed plus 3x cubed, 3x cubed, negative x squared minus an x squared, 0x minus 3x, negative 3x, bring down to 0. Now I'm matching this one, 3x cubed. So what times x cubed gives me 3x cubed? It's just a positive 3. And I take the 3, multiply through 3 times x cubed, 3x cubed. 3 times negative x squared, negative 3x squared. 3 times 0x, 0x. 3 times 1, 3. Don't forget to change all those signs. Hopefully you're remembering your long division here. That's gone. Negative x squared plus 3x squared is 2x squared. Negative 3x minus 0x. Negative 3x. 0 minus 3 is a negative 3. So here's your remainder right there. So this becomes, if you rewrite h of x here, it becomes quotient 3x plus 3 plus remainder, here's our remainder, 2x squared minus 3x minus 3 over our divisor up here, x cubed minus x squared plus 1. Now the definition of your horizontal asymptotes was as x goes to positive, increases in magnitude, positive or negative infinity, does this thing approach something. If you're looking at this right here, your degree of the top is less than the bottom. So what happens is, as x gets increasingly large, this whole piece goes to 0. Because, like, let's throw in a million, right? We have 2 times a million squared minus 3 times a million, anyways, blah, blah, blah. And on the bottom, I'd have a million cubed. Well, this part makes it so much, because we're taking it to the third power. This makes this whole denominator so much bigger than the numerator. It's like a really tiny number up here over a huge number down here. So it's like 0.0000. Anyways, it's going to 0. All this is going to 0. So we're left with right there. That's our slant asymptote right there. Okay, so it's approaching that value. That's our slant or oblique asymptote is your quotient when you do the division. Okay, so that's what that's talking about. Here's another one. Again, do the division right there. So 2x to the 5th minus x cubed plus 2 divided by x cubed minus 1. When you do the division, you're going to have, if you notice, the degree of the top. First of all, I should say that, I'm sorry, I missed this. The horizontal asymptote, degree of the top, degree of the bottom, 5 greater than 3. If n is greater than m, there's no horizontal asymptote. Now in this case, it's 2 more than the bottom. So you don't have a slant or oblique asymptote. What happens is this function will behave like, take the leading coefficient right there, 2, and it'll behave like this power function, 2x, and then you take the degree, 5, minus 3. So it's going to behave like 2x squared. And I actually plugged this into decimals to show you this graph. So if you look here, here's the original function, 2x to the 5th minus x cubed plus 2 over x cubed minus 1. And then there's the power function, 2x squared. Okay, and you notice on this graph, gosh, I can't draw on this. The power function's in blue, the original function's in red, but as x increases in magnitude, can you see how as it goes out, it's approaching the blue line there? Yeah, that's what I mean by it. It just behaves at the extremities like the power function. Now, lastly, we're going to do some more of these in the next section, but what if you have a function like this, 2x minus 3 over 3x squared plus 1. If the degree of the top, which is 1, is less than the bottom, which is 2, the degree of the top is less than the bottom, automatically y equals 0 is your horizontal asymptote. So again, that's because the whole bottom, when you throw in a huge number, is so much bigger than the top. So it's going to be approaching this y value at the extremities. As you go out, it's going to be getting closer and closer to that y value. Again, I don't know exactly what the graph looks like, but that's what's going on with that function. Okay. So one other example I might give you here is, no, not that. If you've got let's say you've got a different function like this, 2x squared minus x plus 1. On the bottom, you got 3x squared minus 4. Okay. If the degree of the top is the same as the bottom, so the degree of the top is exactly the same as the bottom if n equals m, the horizontal asymptote at large values of x, as x increases in magnitude, will approach your leading coefficients, 2/3. In other words, if you throw in a million it's essentially 2/3. It's going to end up being 0.666666, whatever. Okay, it's approaching that y value. Okay, all right, we'll do some more of these. Thank you. We'll see you guys in class. Bye-bye.